Welcome to today's geology tour here at Saguaro National Park. My name is Ryan and I work in interpretation here at the Visitors Center. Today's tour is called The Destruction of Granite, a visual tour describing how the Santa Catalina and Rincon Mountains were formed in Tucson, Arizona. We will also be discussing how we know how these mountains were formed, otherwise known as proof. Because it sure wasn't aliens like the Great Pyramids of Egypt. So let's get started with the tour. So we will begin by prefacing this discussion and eliminating some bad information that is currently out there on this region. If you look to the map on the right-hand side of the page of Arizona, you will see that this area is regarded as basin and range province. Now, it is true that from 15 to 2 million years ago, this area did have basin and range fault, which includes the western aspect of the Catalina Mountains, also known as the Pirate Fault, as well as the eastern aspect of the Rincon Mountains, also known as the Martinez Fault. These mountains were not formed by this process. You do see the classic 60-degree angle of lift on these two faults, but these mountains were created by what is known as a low-angle extension detachment fault, or simply an extension fault. This occurred between 18 and 25 million years ago. Extension faulting occurred from southeastern Arizona all the way to central California. Most of these occurrences brought granite from underneath the surface up slowly towards and above the surface at an angle of lift and under great pressure. Pressure and friction create heat and therefore change the granite to a metamorphic rock, namely Mayanite, microbreccia, and gneiss. So let's dive further into the details and proof of this extension fault process. So what is a metamorphic core complex? So we mentioned rocks like granite, but also sedimentary can have their composition changed under heat and intense pressure. Imagine having 40 kilometers of upper crust on your head. That's what the underlying layer of granite had to deal with. You can imagine that there would be quite a bit of pressure and heat in there. Then the Earth decides to create a low-angle extension fault and drag you through 60 kilometers over 7 million years. What happened? You may look deformed after this, and your composition may change entirely. Once you reach the surface and above, you will begin to dome upwards because of all the intense weight being lifted off of you. Congratulations, now you feel like the Rincon Mountains did 18 million years ago. These metamorphic core complexes generally resemble domes because of the course of the doming effect. So what are the details of this fault system? Let's see. Where there is not a direct answer as to why these faults started pulling the Earth's crust apart, we do know that at some point in the plates that these faults reside on their massive stretching. We do not know why the Earth is stretching, it just is. Originally this area was compressed, so perhaps this is just the natural reaction to that compression, like a rubber band or something of that nature. So the Earth began stretching and formed a fault line here, which is actually viewable in the park itself. The important thing to know about this type of fault line is it is not straight on the surface. In fact, the best thing to do is visualize a lakeshore, and that is what a low-angle fault extension looks like at the surface. Curved, highly variable, and does not fit into our general image of a fault line. So as the Earth stretches, normal faults are created that move up and down like basin and range faults. These are minor faults, and were all filled in with sediment in the Tucson Basin over the next few million years. So, the angles of this fault are the easiest way to prove of the existence or occurrence of this geological process. The upper section of crust, which contained the Tucson Mountains, moved roughly 60 kilometers west of south. The lower or underlying layer of rock moved 60 degrees east of north, or the exact opposite direction. As we mentioned, the pressure and heat was so great that it splintered the rocks at the site of the fault, rendering them unidentifiable over the area of roughly 100 yards. This is the fourth type of rock according to the doctor that mapped the region, known as fault rock. Now let's explore the rise of this fault, which begins our proof of this event. So as this picture shows, the Tinca Verde Ridge rises roughly 20 degrees from ground level. Easily put, if you had a protractor and found a horizontal line at 0, the rise of these mountains would be almost exactly at your 20-degree line on that instrument. Every single canyon wall or front range of the Santa Catalina and Rincon Mountains measures almost exactly 20 degrees. So that lets us know that there is definitely some type of faulting here to account for this uniform rise. Now let's look at some additional proof of this process. Looking at this picture, which is not of this area actually, I am just using it to illustrate the striations that form in the bedrock as a result of faulting. So in the Rincon and Catalina Mountains, nearly every single outcrop of the bedrock will have defined striations 60 degrees east of north. That's 30 square miles of proof showing what direction this fault moved. Do you need more proof than that? We will see some on the next slide. We already have angle of the rise and the angle of movement, so we will see proof of the metamorphosizing event next. All rock has different deposits in it. The granite in these mountains has feldspar, quartz, and mica. This picture shows how, when superheated under all this pressure, quartz melted and became elongated. In our bedrock, the feldspar did not melt and is still in a circular shape. So, there was an intense heat and pressure, but not enough that the high temperatures requiring feldspar to melt. Volcanoes and tectonic plate occurrences typically have temperatures that far exceed the requirement for melting and deposits in it, so one would assume that this was a cooler event, likely a low-angle fault. What do you know? So, we have not only explained the process that built these mountains at Saguaro National Park, but we have looked at the evidence and proved what actually happened. We identified the angle of uplift, the angle of striation and movement, identified what type of fault this was, clarified that it was not basin and range oriented, and identified minerals in the rock that helped us further prove this extension event. I want to thank you all for coming, and I urge you to go forth and spread the good word so that Tucsonans do not continue to be confused about our city's geological history. I hope you have enjoyed this visual tour, and I hope you come back soon. Have a great day.